Okay, we had some technical difficulties, but I think we're going to make it through. So last time we were talking about correlation, and we looked at the example of number of people in the county and the number of property crimes, and then at the end of class we did the number of miles driven and the cost of the car. And both cases we found out that we rejected H0, so we had linear correlation. So let's go ahead and see how we get to use this kind of information. So going back to our number of people and number of property crimes data, which makes more sense to be the independent variable, the number of people or the number of property crimes? The number of people is independent and the number of property crimes would be dependent. So X is the number of people in thousands. And Y is the number of property crimes. Okay. All right. So, and we found out that we have our data here in list 1 and list 2. So let's go ahead and find our regression equation. And remember that we found that regression equation by using option number 8, ln reg A plus BX on list 1 and list 2. And we found out that our regression equation is Y equals 93.71 plus 10.32X. Now, the big deal for using correlation and regression is if there is a pattern and we can find a line that follows that pattern fairly well, we can use it to make predictions. So if we look at Millard County that year had 13.0 thousand people. Notice that I left it in thousands because X was measured in thousands of people. So if we wanted to predict the number of crimes, remember that Y was the number of crimes, we're going to stick 13.0 thousands into the X value of our prediction equation. And let's see what happens when we do that. I get 227.87. So basically, our model would predict 228 property crimes. So let's see that. If we were to come here to where about 13,000 would be, and if we were to come up to the line and go across, yeah, that looks like it'd be somewhere in the low 200s of property crimes. Okay. All right, so how did our prediction of 228 crimes compared to the actual of 280 crimes? It's a little low, but it's fairly close. So our prediction was fairly close. But not exact. Yeah, remember that we put in 13 because X was measured in thousands of people. All right. Well, let's try another county in Utah. Anybody from Salt Lake County? Okay. Well, Salt Lake County had over 1 million people, so that would be 1,168 thousands of people. So let's put that into our regression equation and see what happens. So we would predict that Salt Lake County would have 12,147, if we round to the nearest crime, property crimes. How does that prediction compare with the actual number of 60,515? It's way less, isn't it? So the prediction is way low. All right. So, well, how come it worked for Millard County, but the prediction wasn't very good for Salt Lake County? What's wrong? So if we look at our sample had small and medium-sized counties, where Salt Lake County is humongous. So that brings us to an important point. Should I make predictions on a very large county if my sample only has small and medium counties? No. So we only want to make predictions if we can reject H naught and we stay within the scope of the available data. If we were to look at our scatter plot, here's our scatter plot. If we were to look at where Salt Lake County would be with over 1,000 thousands of people, where would that be on the graph? Way out there. So notice that that wouldn't fit on our data, our scope. In other words, our range of values. Okay. Could I predict like Sanpete County with about 20 or 30,000 people? Yeah, but Salt Lake County, probably not, because our data only had small and medium-sized counties, not large. Okay. And if there is no correlation, in other words, if you fail to reject H naught, do not use the regression equation to make predictions. All right. The next thing we want to do is talk about marginal change. Unfortunately, we lost a little bit of time due to technical difficulties. So marginal change is simply the slope. And our regression equation was 93.71 plus 10.32x. Which number is the slope there? The 10.32. So the marginal change will be 10.32. And what the marginal change tells us is the change in the y value as the x goes up by 1. So we predict that the number of property crimes, the y value, will go up, because 10 is a positive number, by 10.32 for every additional 1, but remember that we measured those in thousands, people in the county. All right. Whew. Oh, okay. So if one county has 1,000 more people than another county, we would expect that the first county, the slightly larger county, will have about 10 more property crimes. Does that make sense? Good. Okay, let's look at example 2, where we had our Mazda Miata data, and we put those in list 3 and list 4. Okay. So let's find our regression equation. So let's come down here to option number 8, linreg A plus BX. And we're going to do list 3, comma, list 4. So our regression equation is y equals 26,909 minus 0.492x. I stuck the A value in for A and the B value, including as negative, in for B. I will try to tell you, in this case, we'll take this to the nearest dollar and this to the nearest thousandth. Okay. But on a test, I'll try to tell you. Okay. Now, if we looked at our graph from last time, would it be good to make a prediction of the cost for a car that's driven 10,000 miles? Yeah, 10,000 is inside the data, isn't it? What about 20,000? Yeah, 40,000? 40,000's get a little iffy, right? What about 50,000? No, because now we're starting to get outside of the data, aren't we? Okay, so 10 and 20,000 miles would be good things to make predictions on. So let's do that. So let's predict the cost of the car. Remember that cost was the Y value. So Y equals 26,909 minus 0.492 times X. X was the number of miles driven, which in this case is 10,000. So let's do that on our calculator here. Let's do 26,909 minus 0.492 times 10,000. So how much would we predict the car costs if it has 10,000 miles on it? Just under $22,000, right? So we would predict 21,989. Now, if I find a car that has exactly 10,000 miles on it, will they be asking exactly 21,989? No, but these are predictions, so they should be close estimates. If somebody's asking $30,000, I'm like, wow, that's overpriced. Or if they're only asking $10,000, then I go, has this been in a wreck or something? So, but these are predictions, and predictions are not perfect, but they usually should be fairly close. What about the prediction for a car with 20,000 miles? Should be lower because more miles. Okay, the car's used up some more, so it's worth less. So I get about $17,069. Okay, that's maybe a little bit more in my price range as a teacher. Once again, it's not going to be exactly that amount, but it gives me a pretty good feel. Where did 26,909 come from? Our regression equation. Oh, actually, that's a good question, Michael. What would that mean? What if X was 0 miles? What would 0 miles mean? A new car, right? So we would predict that a brand new car would cost about $26,909. Ah, cool. So nice. I'm glad you noticed that. What's that? Okay. Are these predictions? Are they always exact? They're not always exact, but they give us a pretty close number. A is what we call the y-intercept. So if X is 0, what would we predict for the price of a car with 0 miles? 26,909. I know this one was a little bit higher, but maybe this one has a leather interior. So miles driven is not the only factor in cost of a car. Maybe there's premium sound system or leather interior or things like that. Okay. So let's talk about the marginal change. Who's the marginal change? Who's the slope here? Negative 0.492, right? And how would we interpret this? we predict that what's the Y variable here? Cost of the car what's that, Zach? Will go down. Why'd you choose down? Last one it was up. Oh, we have a negative slope. So we'll go down by 0.492 or 49 cents for every mile driven. So what that's saying is, for every mile that I drive the car, the cost of the car goes down by about 49 cents, almost 50 cents. Okay. So if I put on 10,000 miles, I expect it to go down by about $4,900. Okay. If I put on another 10,000 miles, I expect the price to go down by another $4,920. Does that make sense? All right. Okay. All right. Thanks for bearing with me with our technical difficulties. I do want to give you some time to work on example 3 and 4, but I want to do something that I hope will help you. Okay. So let's take a minute here. And did the flow chart help on the last test? Yes? Oh, okay. All right. So for the last test, we had a flow chart, and even the one before that. So I'm just going to take a few minutes here, but I think this would be well worth the time. So let's go ahead and take a look at this flow chart. Now I've adapted it a little bit so we can talk about chapters 7 through 10. So the first, when I'm studying one of these statistics kinds of questions, I ask myself how many samples and what type of data I have. So over here, if I have one sample, it can be a mean or a proportion. Okay. Then I'm going to use the chapter 7 through 8 flow chart. In other words, the one we worked on previously. So we ask ourselves, is it a confidence interval or is it a hypothesis test? Are we dealing with the population proportion from a binomial, or are we dealing with a mean? Things like that. So that we've already done. What's the new stuff that we've talked about here over the last 2 chapters? 2 samples. Okay. And if we take 2 samples, we want to ask ourselves which parameter. Are we dealing with a proportion from a binomial? If so, what requirements do we need to check? Yeah, so we need 2 random independent samples. And what else do we need? Dedication, yep. And the number of successes and the number of failures are greater than or equal to 5 on each sample. Zoom that in just a little more. There we go. That's a little bit better. If we did that, if we did that, which programs were we running when we had 2 samples and proportions and we met the requirements? 2 prop z test and 2 prop z ins. How do we know which one to use? if it's a test or an interval. It's that easy, right? Since it's a proportion and a binomial, and we had number of successes and failures greater than or equal to 5 on each sample, then it's close enough to the bell curve because of the normal approximation to the binomial that we did in 6.6. Remember that big, scary, ugly thing? That was big, ugly. Okay, so that was a proportion or a binomial for 2 samples, and we did that in 9.1. In addition to doing proportions, what else have we been studying? On which other parameter? Mean, good. And remember that a mean needs to have ratio level data, or at the very least, interval level data. Okay. Now, when we had the mean, we actually had another question that we needed to ask ourselves. What was the next question that differentiated 9.2 from 9.3? That was part of the requirement check, but not the difference here. Is it paired or not? Good. So is it dependent samples? In other words, that was our paired data. If it was paired data, there must be a link between corresponding data values. And so we did list 3 is list 1 minus list 2. And while we're at it, let's do our requirement check for that. We need to have a random sample of dependent data. And let me slide this up just a little bit for our people in the back here. What else did we need? Michael was talking about something. Ah, good, Miss Sagers. N is greater than or equal to 30 or normally distributed. So those were our 2 requirements. And if that was true, then we did a t-test on not list 1 or list 2, but on list 3, their difference. Or we did a t-interval on list 3. Good. Now, in 9.2, we talked about, remember watching SpongeBob? So we had independent samples, okay, meaning that there is no link between our data values. And what requirements did we need to check there? Two random and independent samples. Good. What else? How do we know? Yeah. So we need N1 and N2 to be greater than or equal to 30, or both samples are normally distributed. And which programs did we run with that scenario? Two sample t-test and two sample t-ends. Good. Now, I know the calculator has two samp z test and two samp z int, but why are we using t distribution? We don't know the population standard deviation. Okay, good. And finally, what have we just been doing the last two classes? Correlation and regression. So we're working with bivariate data. So remember that these were our scatter plots. And to do our hypothesis testing here, we needed to have, as always, a random sample and what else?
Oh yeah, we get rid of the
Outlier errors. Good. So we need to have a random sample. The scatter plot should look something like a line. Okay. And we remove outliers if we know they are errors. Okay. Like somebody who is 600 inches tall or 6 inches tall, right? We would definitely know those are mistakes. If that's true, what program do we run? The linreg t-test. Okay. Now you can use the linreg a plus bx, but that won't do the hypothesis testing. That will only get you the equation. Okay. All right. So hopefully that helps us now kind of put into the big picture what we've been focusing on here the last 6 or 7 weeks. Okay. And the final exam, 60% or so of it will be hypothesis testing and confidence intervals. So a good part of that, because that's the real meat and potatoes. Now, that still leaves 40% for probability and nominal and ratio and binomials and normal distributions and things like that. Okay. All right, so in the remaining about 10 minutes that we've got, despite our technical difficulties today, I want you to do example 3 and 4. So finish this guy up, and I'll send out an email with a link to this. I'll have to upload it to YouTube, but we'll get that done so our people who tried to join remotely can actually hear something. So for some reason, we had some nasty technical difficulties today. I'm not sure why. All right. So I did a little bit of work here. So here is my scatter plot, and I ran the hypothesis test. So we'll show you my work here. And I've got a p-value of 0.1146. Okay. So how does my p-value compare to alpha of 5%? Greater. And if the p is greater than alpha, what's our conclusion? Fail to reject. Is this data close enough to a line to use a line to make predictions? No, it sort of looks a little bit, but not all that close to a line. So we probably shouldn't be using our line to make predictions on this stuff. Okay. All right. We'll see you on Monday.